All right, let's dive in. Today, we are pulling back the curtain on a really cool data structure, the AVL tree. It's a classic for a reason. We're going to figure out, why does this thing even exist? How does it pull off its amazing self-balancing act? And maybe most importantly, where is it secretly running the show in the tech you probably use every single day? Okay, so here's how we're going to break it down. First, we'll look at the big problem with regular search trees. Then, we'll meet our hero, the AVL tree, and see how it solves that problem. We'll get into its secret weapon, the balance factor, and the cool moves it makes, called rotations. And finally, we'll tie it all together and see why you should actually care about any of this. All right, first things first, we have to talk about the unbalanced tree problem. I mean, this is the whole reason AVL trees were invented in the first place. It's all about how a data structure that's supposed to be super fast suddenly isn't. So let me ask you this. You know how binary search trees are legendary for being fast, right? For being super efficient? But what if they just weren't? What if I told you there's a way for them to become painfully, horribly slow? Okay, so here's the Achilles heel. Picture this. You're feeding sorted data into a standard binary search tree. You put in 10, then 20. Well, that goes to the right of 10. Then 30 goes to the right of 20. Then 40. You see the pattern here, right? We're not getting this nice, bushy tree. We're getting this long, pathetic, stringy chain. And boom, that's the nightmare scenario. What we've built isn't really a tree at all. It's just a glorified linked list. And that means our search time just went off a cliff. It went from O of log n, super fast, like flipping through a phone book, to O of n, which is like reading that phone book from the very first page until you find the name. It's a total disaster for performance. Okay, so that's the problem, and it's a big one. So how do we fix it? Well, this is where our hero steps in. It's time to talk about the AVL tree. So what is an AVL tree, really? Think of it like a regular binary search tree, but with a built-in superpower. It watches itself, and after every single time you add or remove something, it automatically checks and rebalances itself. It's like having a self-correcting system that guarantees it will never turn into that slow, lopsided chain we just saw. And a little fun fact for you, the name AVL, it just comes from the names of the guys who invented it, Adelson Velsky and Landis. Okay, but how? How does it know when it's out of balance? It's not just magic. It all hinges on one single incredibly elegant rule. This right here. This is a secret sauce. It's called the balance factor, and it's so simple. For every node in the tree, you just do one little bit of math. Take the height of the left side and subtract the height of the right side. That one number tells you everything. It's the tree's personal health check. And here's the rule. It's simple. As long as every single node in the tree has a balance factor of -1, 0, or +1, everything is great. The tree is considered balanced. +1 means the left side is a little taller, -1 means the right side is a little taller, 0 is perfect harmony. But the second a node's balance factor hits a +2 or a -2, that's when all the alarm bells go off. The tree knows it has a problem and it's time to fix it. So what happens when those alarms go off? What does the tree actually do? Well, it performs this really cool self-correction. It uses a series of moves called tree rotations. This is where the magic happens, so let's check them out. Okay, case number 1, the left-left imbalance. This is pretty straightforward. The tree is too heavy on the left because a new node got added to the left side of the left subtree. I mean, you can practically see it tipping over. And the fix? Oh, it's beautiful. It's just one move, a single right rotation. The problem node kind of pivots down and to the right, and its child moves up to take the top spot. Bam! One move, and we're balanced again. All right, next up, you can probably guess this one. It's the right-right imbalance. It's the exact same idea, just the other way around. The tree is too heavy on the right because the new node was added way down the right side. And the solution is, yep, exactly what you're thinking. A single left rotation. The top node pivots down into the left, its right child comes up, and everything is back in balance. Super simple, super effective. Okay, now things get a little more interesting. The next two cases are a bit trickier. First is the left-right imbalance. So the main node is heavy on the left, but the new node was added to the right side of that left child. It creates this kind of awkward zigzag shape, and a single rotation just isn't going to cut it here. So we need a two-step move. It's pretty clever, actually. First, we do a left rotation, but on the child node. And what this does is it magically transforms the whole problem into a simple left-left case, which we already know how to solve. So then, step 2, we just do our standard right rotation on the top node, and that zigzag gets completely ironed out. Problem solved. And our last case, number 4, is the mirror image of that one, the right-left imbalance. The tree is too heavy on the right, but the problem came from an insertion on the left side of that right child. Another one of those zigzags. The solution? You guessed it. It's the same logic in reverse. First, we do a right rotation on the child, which turns this mess into a simple right-right problem. Then, we do a left rotation on the parent to finish the job. And that's it. Those 4 rotations, left-left, right-right, left-right, and right-left, are all an AVL tree ever needs to fix itself.
Okay, so we've seen the disease and we've seen the cure. But you might be thinking, man, that seems like a lot of work. Why bother with all this balancing stuff? Well, let's talk about why it's so important in the real world.
When you get right down to it, it's all about a trade-off. A regular binary search tree, sure, it's easier to code, but its performance is a gamble. It can be fast, but it can also get really, really slow. The AVL tree, on the other hand, is a bit more complex, no doubt. But in return, you get an ironclad guarantee. It promises you that it will always be balanced, and that searching, inserting, and deleting will always be incredibly fast. Always O of log n. And that guarantee is not just a nice to have, it's absolutely critical for some pretty important stuff. We're talking about the indexes that make your database queries fast. We're talking about how operating systems manage memory or how file systems keep track of all your files. Basically, any situation where you absolutely cannot afford for lookups to suddenly slow down, that's where you'll find something like an AVL tree doing the heavy lifting. So to wrap it all up, an AVL tree makes a deal. It takes on a little extra work, a little overhead from all those rotations in exchange for that rock-solid performance guarantee. Which leads to a really interesting question, doesn't it? What if you're okay with a slightly less strict balance? What if you could get almost the same speed, but with a little less rebalancing work? Well, that's where things like red-black trees come into play. But that's a whole other story for another time.